This is number 48 in chapter 16. That's looking at how a buffer responds to different stimuli as far as adding acid or adding base. And so we have a 100 milliliter solution that's 0.175 molar in HOCl and 0.150 molar in sodium hypochlorite or NaOCl. And we're asked a couple of questions. First, we're asked for a pH initial, and then we're asked to solve a few others. So the first thing, again, we got to look up that Ka from our table, and that's 2.9 times 10 to the negative 8. And we also have to write our equilibrium with regards to the parent. So the hypochlorous acid, or HOCl, is our parent acid, and that's reacting with water in an equilibrium to produce hypochlorite and hydronium ions. The first question is asking us, what is the pH initial? Essentially, we have these two concentrations of acid and conjugate base. What is the pH? And so I'm not going to use the ice table, which you can, but again, we can simply use the Henderson-Hasselbalch since this is a buffer. And so we can solve for that pH, which would be equal to the pKa, which is a negative log of my Ka. We had to look that up. Plus the log of my concentrations. I have 0.150 molar for my OCl, and I have 0.175 molar for my HOCl, or my hypochlorous acid. So that pH is going to be equal to 7.537 plus the log of 0.857, which when you take the negative log, when you take the logarithm of, is negative 0.0699. And so that gives us a pH of 7.47 initially. So we take these two buffer components, we take our acid, we take our conjugate base, we mix them up with these concentrations, and that is our pH simply using the Henderson-Hasselbalch. Again, you can use an ice table if you want. And so for part B, it's like, what is the pH now after we've added 150 milligrams of HBr? So we're adding strong acid, and so what we always want to realize with a buffer is that whenever we add acid, extra strong acid, or extra strong base, it's simply going to change the initial concentrations of my parent and my conjugate. So in this case, I'm adding HBr, which is a strong acid, and so the strong acid is going to react with my conjugate base to turn my conjugate base, after it gets protonated, into my parent acid. So basically, we're changing the mole values of our constituents of our buffer. So we have to figure out how many moles of HBr, right? Because the moles of HBr is also going to be equal to moles of that H+. So if we take our 150 milligrams of our HOBR, right, we have to, realize that that's milligrams. Let's get that into grams. So we do that simple conversion and then divide that by its molecular weight. And so that's how many moles of HBr we've added, right? But that's now going to invoke a conversion of conjugate base into parent. So we need to figure out how many moles of each one of these constituents we have. So if we take our concentration of our HOCl, use our volume, we can get our concentration of our mole value of our acid. And if we do the same thing for our conjugate base, we can get its mole value as well. So these are the initial mole values, but again, this addition is going to affect those. So it's going to affect it by reducing the amount of moles of OCl and increasing the amount of moles of HOCl. Again, that's because OCl is becoming protonated by the addition of HBr to form more HOCl. So we would take our 0.015 moles of OCl minus, and we would subtract from that our hydroxide. And so that gives us a value of 0.0131 moles of OCl. And we want to do the same thing for our parent acid, but we are going to add that value of hydroxide to get our new mole value of HOCl. So again, we just converted our parent acid and our conjugate base into their mole forms, and since the addition of HBr is reacting with OCl to form HOCl, that's why we subtract that amount of hydroxide from OCl and we add that amount of hydroxide to HOCl. So to make some more room here, we have these new mole values, 0.0131 moles for our OCl, and we have 0.0193 moles for our HOCl. Now that we have the new mole values, we can now convert those into concentration by dividing by the volume, the 0.1 liters. And so we're going to do that for both of them. And so those are our new concentrations. And so we're going to use the Henderson-Hasselbalch equation again. And so that pH is equal to the pKb. In part A, we already figured out that's 7.537. And now plus the log of these new concentrations. That means our pH is then going to be equal to 7.537 plus then the negative 0.168 after we take the logarithm of that ratio to give us now a pH of 7.369. So we went from 7.47 to 7.36, 7.37. So we're still within that buffer's capacity, but we do see a slight change. So again, the addition of acid changes, in this case, the amount of conjugate base by decreasing it. It also changes the parent acid by increasing it, again, according to that top reaction. Part C is looking at now the addition of not acid, but of base. And so really we're going to use all the same steps that we did for part B in part C, but it's a little bit different, right? So we're adding 85.0 milligrams of sodium hydroxide. And so now, instead of what we had in part A, we have the opposite process. The sodium hydroxide is going to react with the acid, the parent acid, and convert it into the conjugate base. So the exact opposite to what we saw in part B. But the steps are the same, meaning that we need to get this value into moles. And so we get 2.125 times 10 to the negative third moles of hydroxide. From part B, we already figured out the mole values of our HOCl. And so we are going to subtract that value. To get our new mole value for HOCl, 0.0153 moles. And we're going to do the same thing for our conjugate base, but we are adding that value to get our new mole value of OCl minus. So those are our two new mole values, again doing the same thing that we did for part B, except again we're reacting now with base. So we'll begin there. We had that 0.0153 moles of the HOCl, and we convert that then into our molarity. We want to do the same thing for our OCl minus. And so now we can solve for, again, the pH using the Henderson-Hasselbalch. That pH is equal to 7.537, which we've done earlier, plus the log of that ratio, 0.171 over 0.153, which equals 0.0483 as far as the logarithm of that ratio, and that gives us our pH, which is 7.585. So again, the addition of now strong base does affect the pH. We see a slight increase from 7.47 to 7.58, but again, we're still well within the range of the buffer's capacity. But notice that there is a slight change depending on if you add strong acid or strong base. We added strong acid, there was a slight change to a more acidic pH. When we added strong base, there was a slight change to a basic pH. And so that's a good way to maybe check your answer as well. That is number 48 in chapter 16.